In this video, we're going to take a look at integrated rate laws once again. Here we're going to actually do calculations with our equations and solve for, say, the concentration after a reaction has run. As a reminder, here are the set of equations we looked at in the first video. For each different order of a reaction, we have a different integrated rate law, that's those guys, and we have a different half-life equation, that's those. Remember that you are responsible for memorizing which of these equations goes with which order. You'll be given the equations, but you should be able to identify that this is my second order integrated rate law, this is my first, and this is my 0th. Okay, let's solve some problems. Here, this says the reaction of butadiene gas yields C8H12 gas, and it's described by this equation. This dimerization reaction is second order with a rate constant equal to 5.76 times 10 to the minus 2 per molar per second, under certain conditions. If the initial conditions of butadiene is 2.0 molar, what is the concentration after 10 seconds? Okay, so what do we do here? Well, I've broken our process down into a few steps. The first step is we need to determine the rate order. Sometimes it just straight up tells us, and that's nice. Other times it doesn't. We have to use the units on the rate constant or a graph to determine the rate order. In this case, it just says it's second order. So that means we want to go and grab our second order equations. In particular, we want to grab the one that's going to solve for concentration after 10 seconds. So that's going to be this equation. It's second order, and it relates concentrations to time. Next, we're going to write down the knowns and unknowns. So what do we know, and what are we looking for? Well, the very first thing it tells us is the rate constant. Remember, that's K. So we know K equals 5.76 times 10 to the minus second per molar per second. The next thing it tells us is that there's an initial concentration of butadiene. Remember, that's this one. That's 2.0 molar. So my concentration of C4H6 initial, that's the 0 one, and that's important to label because you'll get a different answer if you plug that into T, is equal to 0.2 molar. Lastly, it tells us a time after 10 seconds. What are we looking for? We want to know what the concentration is after 10 seconds. So what we're looking for then is C4H6 at time T. So now I've written down my knowns and unknowns. Now I need to rearrange my equation to solve for my unknown. In this case, my unknown is AT, the reactant concentration at time T. So I already have an equation that's set up to solve for that. True, it is set up to solve for 1 over AT, but we'll take care of that at the end. So 1 over AT equals 1 over my initial concentration, which is 0.2 molar, plus K, which is 5.76 times 10 to the minus 2, times time, which is 10 seconds. Now I want to plug that into my calculator. So I'll do 1 divided by 0.2 plus 5.76 times 10 to the minus 2 times 10. When I plug that into my calculator, you should get 5.576. Now, the last step here is to rearrange to solve for AT. What that basically means is that I need to do 1 over this guy. So you can think about this in terms of doing algebra where you moved AT up here by multiplying by AT, and then you moved this down there by dividing by 5.576. Alternatively, you can just say, hey, I know that I need to take the reciprocal of this to get the concentration at time T. So 1 over 5.576 is going to be equal to AT. And if you plug that into your calculator, you will get 0.179 molar. So notice the concentration dropped. That makes sense. We started at 0.2, and now we're down to 0.179 after 10 seconds. If we let the clock continue to run, that concentration would continue to drop. Let's take a look at our next reaction. In this reaction, we're looking at the decomposition of cyclobutane. So they all have fancy names, and they'll put things like decomposition or dimerization, but none of that really changes the fundamentals of the calculation. The point is we have C4H8 going to C2H4, and we're given some information. It says if the final concentration of cyclobutane was 0.3 molar after the reaction ran for 120 seconds, what was the initial concentration? Well, in this case, we need to start with, once again, determining the rate order. It doesn't actually tell us what the rate order is right off the bat, but it does give us the units for rate constant. And remember that if the units for rate constant are per second, that tells me that I have a first order reaction. So I have down here written the equation for the first order reaction. Okay, the next is to write my knowns and unknowns. So what do I know? Well, it tells me the final concentration. So that's going to be C4H8 at time t. And I know that's 0.3 molar. It also tells me that the reaction ran for 120 seconds, so that's time. And it's asking me for the initial concentration. It wants to know, where did I start? So this is going in a different direction from the last one. Before, notice I started with my initial reaction concentration and worked towards the final. Now it's saying, oh, okay, you've arrived at 0.3 molar after 120 seconds. Where did we start? All right, so the next step is to rearrange to solve for my unknown. What I want to solve for is this guy. So what I need to start by doing is adding KT to both sides to start to get that by itself. So we'll do that. Go back to red now. And we'll get ln of A at time t plus KT equals ln of A initial. So we're starting to isolate that initial concentration. Now, here's a really important step. To get rid of the natural log, we have to do its opposite. Its opposite turns out to be E, the E on your calculator that stands for exponential. And so what I have to do is E raised to both sides to get rid of the logs. So that might seem new to you. And if it does, just remember that to get rid of logs, we have to do the opposite. For natural log, it's E raised to. For log base 10, which is just written as log, it's 10 raised to both sides. So that gets rid of my log, and I write my new equation, E raised to ln of A at time t plus KT. And now that's all equal to my initial concentration. Notice I did E to that whole left side, not just one part of it. So writing parentheses here is a good idea. All right, so now all I got to do is plug in my equations. So log of my concentration at time t is 0.3 plus K, which we know is 9.2 times 10 to the minus 3. It's right up there. Times T, which is 120. So in your calculator, you want to first do log of 0.03 plus 9.2 times 10 to the minus 3 times 120. Take that answer, and that's what you want to put in the exponent of E. If you do all of that correctly, you should get 0.90 molar. So try that out in your calculator to make sure you get the same thing. Okay, one more problem. Here, we're given the rate constant for a decomposition reaction, the same one we looked at before, and we want to know the half-life. So this problem is looking for the half-life, so we need to go grab a half-life equation, and we need to grab the correct one. What's the rate order? Well, just like we saw last time, because the units of our rate constant are per second, we know that the reaction is first order. So that means we go and grab this half-life equation. This problem is pretty straightforward. We just need to write down our knowns and unknowns, but there's only two of those. So the known is K. It's equal to 9.2 times 10 to the minus 3 per second. And the T1/2, that's what we're looking for. So all I got to do is plug my K in there and solve for T1/2. That's my half-life. So 0.693 divided by 9.2 times 10 to the minus 3. One note here, when you plug that into your calculator, make sure that you use parentheses on the bottom. If you don't use parentheses on the bottom, your calculator may end up multiplying by that instead of dividing by it, depending on exactly how you put it in. But if you use parentheses, you'll get the right answer. So check that out. Make sure you do. It's 75 seconds. So that is how we use our integrated rate laws and our half-life equations to solve problems.